10.3. Inscribed, if I can spell, angles. Okay. Previously, we have been working on central angles. Okay. What is the relationship between a central angle and the intercepted arc? They're the same. Good. They're exactly the same. Today, we're moving on to what is called an inscribed angle, which would be this. What do you notice about this? It's not in the middle anymore. Where is it? On the circle, right? Okay, it actually touches the circle. So if I were to take this and put it here, is that inscribed? No. It has to be touching the circle. Okay, so this would be an inscribed angle. This would be what we call the intercepted arc. And I went ahead and used that word a second ago, and you guys already knew what I was talking about, so I don't think that'll be too difficult for you. Okay. First thing we have really is a theorem. It's called the measure of an inscribed angle. Would you like to rephrase that?
Can I please have a new paper?
Sure, not a problem.
Thank you.
Sure, Ryan. All right. I'm not going to write exactly the words that they have. What you need to know for this theorem is that an inscribed angle is 1/2 of its intercepted arc. An inscribed angle is 1/2 of its intercepted arc. So, if I have this, what equation could I set up to justify it or to match that statement? Jacob? Good. I'm going to write it the other way around, okay? Just so it goes with this, but you're correct. 100% correct. Okay, angle ABC is 1/2 of arc AC. Which is the same thing he said. He just said it flopped around. He said the arc first, but he said the same thing. Okay. No, it wouldn't be. I just use the 3 letters because in some of these diagrams, you might have things at the same vertex. Yeah, no, angle B would be fine. Taylor? Will it give us the arc? Well, that's what we're going after. So it's going to give you different things at different times. So if it tells you that the arc is 100 degrees, what's the angle? 50. If it tells you that the angle is 30 degrees, what's the arc? 60. Okay, it'll give you both directions. Okay, good question. Now, we have to know this equation also. Okay, don't just think that you can do it all mentally, because sometimes they might give you something like this. They might tell you that this is 40 degrees, but that arc is 5x plus 7 degrees. What's x? Okay, probably not as easy just to do in your head, right? Okay, so Carly, what equation would I set up here to solve it if my angle and my arc were these? Good. 40 equals 1/2 5x plus 7. Okay, because the angle is half the arc, right? Okay, so do it just like you would say it. Now, we've done problems like this in the past. Is it easier to distribute this 1/2 or to just divide by a half and get rid of it? Divide. Otherwise, you end up with a whole bunch of fractions, right? Okay, so if I divide by 1/2, what's that the same thing as doing on the other side? Multiplying by 2, because if you divide by a fraction, you actually multiply by the reciprocal. Good. So 2 times 40 is 80 equals 5x plus 7. I'm going to stop there. You could finish that out if you needed, right? Yeah? Okay. Taylor?
Can we just start that with that since we already know that?
Yeah, you could if you thought of it that way. I personally don't like to change the equation. I like to use that same equation. And then if I have to move things, I can. But yes, you could start out just like that. I'm going to back out of here so we just have the theorem posted on the slide. Okay. So let's take a look down here at example 1. Okay, we'll just roll through these real quick. I won't write them on the board or anything. Example 1, part A. What is the measure of arc STQ? Raise your hand when you can tell me that, please. Go ahead, Paige. 180 degrees. How'd you know?
Because the angle is 90.
The angle's 90, and the arc's twice that, right? Okay, Tamaya, what's the on part B? What's the measure of arc ZWX? 230 degrees. Good. Brian, what's the measure of angle NMP in part C? $50 degrees. Good. Not too bad, right? Okay. So let's move on to example 2. Looking at example 2, notice that there's multiple angles there, right? Do they all share the same intercepted arc, though? Yes. They all intercept arc BA, correct? Or AB. Right? Everybody see that? So, Taylor Stokes, what is the measure of angle E? 30 degrees. Travis, what is the measure of angle D? Stay with us. 30 degrees. And Austin, what's the measure of angle C? So if I have multiple angles and they share an intercepted arc, what do you know about those angles? They're all going to be the same, right? That's your next theorem. This doesn't technically have a name. We've just been calling it 2 inscribed angles. Just so we can pick out when to use this theorem. Now, on this, the names don't really matter again because we're not doing proofs anymore, right? Okay, so the names aren't necessarily important. Thanks, buddy.
Yep.
We'll see you later.
See ya.
Okay, so this theorem says that if 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. Two inscribed angles intercept the same arc. Then they are congruent. Getting some notes there, Gavin? So you can put your diagram on there if you'd like to. Okay, so I have A, B, C, D. Lainey, which angles in that diagram are congruent to each other? Which ones? C and what? C and B, good. Angle B is congruent to angle C because they share the same arc. Okay, they're both inscribed angles and they share the same arc. They must be congruent to each other. So on example 3, before we actually talk about it, what is the shared arc? GH is the shared arc. Matthias, what is the measure of angle F? That would be, if the arc was 75, then the angle would be 37.5. But if the two angles, E and F, they share the same arc, right? So they have to be what to each other? So it's 75. And I know that diagram is actually kind of hard to see which angle that 75 actually goes to. It's a little difficult to see. Okay. We okay with that? Okay. So let's flip page 615 there, the top. They give us two new terms. And I'm not going to have you write those down necessarily. One word is inscribed, which kind of sounds like inside, right? Okay, and the other one is circumscribed. So when I have multiple things, multiple shapes, okay, so maybe one's a circle and one is a polygon of some sort. That polygon is said to be inscribed inside the circle. Notice it's inside, right? Now, it also has to have every vertex touching the edge of the circle. So if I were to draw another circle over here and draw this diagram in here, is that triangle inscribed in the circle? No, because not all vertices touch. Okay? So this green polygon would be inscribed in the circle. The circle is said to be circumscribed around the polygon. Okay, so just don't get those two words confused. Inscribed is what's on the inside. Circumscribed is what's on the outside. Okay. So with those two words, we have two more theorems, and it's the last two theorems we have. If I were you, I would just say inscribed polygons, and then just number them 1 and 2. Okay, the first one you can see is really long. We're not going to write that whole thing out. So let's get this diagram up here, and then we'll talk about it a little bit. So I have a circle with a diameter and then 2 more chords. Making what type of shape? A triangle. What we are going to write does not specifically call that a triangle, but I need you guys to understand that this only works with a triangle. Okay? Now, before I actually write this theorem, what is that? It's a semicircle, right? So, what is the measure of this arc? 180 degrees, right? So, if that arc is 180, the inscribed angle must be 90, right? Because it's half the arc. Everybody agree with that? Okay? So that's actually the reason why this theorem works. But what this theorem says is that angle B is a right angle if and only if AC is a diameter. Again, that's because it then makes a semicircle, right? Making the arc 180, and we know the inscribed angle is half of that. Okay, so it only makes sense that this would actually be a right angle. We ran into the words if and only if again the other day. What does that mean, if and only if? It means that it's biconditional. Okay, so it does work both ways, correct? So it could say angle B, if you might know that angle B is a right angle, and then you could tell that AC is a diameter, right? Or if you knew AC was a diameter, then you would know that angle B is a right angle. Okay? Only works with what type of shape? Triangle. Now, is there a possibility that maybe you have that and then this? Yeah. So here you probably see a quadrilateral, but it's split into 2 triangles, right? Okay, so it still works there, so just be aware of that. Okay. All right, let's take a look at example. It's kind of like example 5. I'll just do one here. Wait a minute. I didn't do the second theorem, did I? Oops. Let's do theorem number 2 first. Getting ahead of myself. Theorem number 2. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Bless you. And as you are writing that, could somebody please remind us what supplementary means? They add up to 180 degrees. Good. Notice that specifically says quadrilateral, right? Okay. So, what statements can I make? Okay, so it could be both ways, right? Since it's if and only if, it could be biconditional. So you might know that it's inscribed in a circle, and then you would be able to tell me the opposite angles are supplementary. Or it might tell you the opposite angles are supplementary, and then you would know that it has to be inscribed. Okay, Amanda, what is set up something that's supplementary for me. Can you do that? What angles? Are they opposite each other in the shape, not in the circle, in the shape? B and D, good. So angle B plus angle D would equal 180 degrees. Okay. Lainey, can you give me another one? Well, we already gave you these ones, right? Good. Angle A plus angle C equal 180 degrees. Oops, not what I wanted to do. Also not what I wanted to do. Okay, everybody agree with those two statements? Okay. Are there any other pairs of opposite angles? No. Only two pairs in a quadrilateral. Not unless, the question was, does a linear pair work? Not unless you know. No, it wouldn't actually. Because a linear pair would be like angles 1 and 2. Those are a linear pair. Okay? Well, I think what you're thinking is these being supplementary. Okay? Those aren't a linear pair, but that only works in special quadrilaterals, like a square, a rectangle, stuff like a rhombus. Okay? So not all the time. Sometimes, but not always. But this will always work. Okay? Let's take a look real quick at a couple examples. We only have 2 examples left. First one I think is going to be fairly easy and short. Second one is fairly long. Okay? With an idea that I got to refresh you on. I need to solve for x here. Carly? So not only is it a triangle, but this side's a diameter, right? Okay. So Carly tells me that 3x has to equal 90 degrees, which is our theorem, right? So then what does x equal? X equals 30. Not too bad there, right? Again, if you have a triangle and one side is a diameter, the opposite angle must be a right angle. Alright, bear with me on this last one. This last one's a little bit longer. Okay, I have a circle with a polygon inscribed inside of it. Happens to be a quadrilateral. It doesn't really matter what these are. So A, B, C, D. And I know that the angles are 10y, 19y, 40x, and 22x. Those are all degrees because they're angle measures. They want to know what are the values of x and y. Okay. Jacob, what do you notice about this? Okay, that's true. The opposite angles are not the same variables. Is it inscribed? Is it a quadrilateral inscribed in a circle? Yeah, so does our theorem still apply? Yeah, so Royal, set up a theorem or an equation for us. Everybody agree with that? That's true, right? Because opposite angles are supplementary. Is there another one I can set up, Seth?
19y plus 22 equals 180 meters.
Now back to what Jacob told us. This is a problem because like he said, the opposite angles have different variables. When I set this up, I have two variables in one equation, right? And I have two variables in this equation. Okay, that's usually an issue for us, except last year you learned a way to solve this. And I know you learned a way to solve this, so don't tell me you didn't, because I actually taught this lesson for Coach Cole one day. So I know you learned it. Now, remembering it, I don't know how long you did it, okay? So we're going to refresh our memories here. Think you know what to do, Royal?
Can you substitute the 19y for 40x, something like that?
You're close. We are going to have to use a substitution of some sort. But before we substitute, we want to solve one of these equations for a variable. Okay? Now, you want to do the easiest one, right? Obviously. So let's think about this for a second. Let's say I solve this equation for y. So the first thing I would do is subtract 22x, right? And then I'd divide by 19. So over here I'd get a fraction, 22 over 19. Not going to be very easy to work with, right? Hey, let's say I solve it for x. I subtract 19, and then I divide by 22. Do I still have a fraction? Yes. Probably not very easy, right? Okay, so let's go up here. Let's say I solve for y. Okay, or even, let's actually do x first, because that x isn't going to be one that we want. I solve for x. I subtract 10. I divide by 4. I end up with 1/4. Probably not very easy to work with, right? But if I take and solve for y, I subtract my 40x, and then I divide by 10. Can I take 40 divided by 10 pretty easy? Yes. Okay, so that's the route we're going to go. Amanda?
So when you subtract it, you just get rid of the variable?
No, it goes with it. Good question. The variable goes with. Okay, we'll do that here in a second. Okay, so let's go ahead and do that. We found our easiest one. Okay, now, if you chose one of the fraction routes, would you still get the same answer in the end if you did your math correctly? Yes. Most of us just like to try to avoid fractions. Okay, so we're going to take this one. I'm going to subtract my 40x. So I actually have 10y equals negative 40x plus 180. Everybody agree with that, what I have there? Okay, and then I divide by 10. So I get y equals negative 4x plus 18. Okay, now, I have solved for a variable, right? Now, it's not an actual number like what we're looking for in the end, but I do have y by itself. So now that I have y by itself, I can take that and plug it in for y, couldn't I? Because that's what y equals. Okay, so let's do that now. So now I have, I'm going to scoot this up real quick. Up and out of the way a little bit. I have 19, but instead of times y, I have times negative 4x plus 18 plus 22x equals 180. What do I do here? Distribute, good. 19 times negative 4 is negative what? 76, good. X, right? Plus 19 times 18 is what is it, 342? Plus 22x equals 180. Can I combine my x's? Okay, so what is 76, negative 76 plus 22? Negative 54. And I'm going to do what with my 342? Subtract it. What's 180 minus 342? Okay. And now I do what? Divide by negative 54. X equals 3. Now I get that's a lot of stuff going on there just to get x equal to 3, right? Okay. And don't let the big numbers freak you out. Okay, that's okay. You can work with those numbers. Now, I know what x equals, right? So, does it matter where I plug it back in to figure out what y equals? No, you could plug it in here. You could plug it in here. I'm going to suggest to you that you plug it in here. Because I already solved this for y, right? There's not really any solving. There's just a little simplifying. So if I were you, I'd take this and I'd plug it right in there. Okay, and we get y equals negative 4 times 3 plus 18. Negative 4 times 3 is negative 12. Plus 18 is 6. So my final answer, x equals 3, y equals 6. Okay. What if they would have asked you to solve for the angle measures? Yeah, you'd take those numbers and you'd just plug it back into your, up here, right, for your angles. Okay, so just be aware of that.
You don't need to find one angle, so you can just figure out that one.
Yeah, it'd probably be easier just to plug it in, but yeah, you'd have to figure out two. You'd have to know that one and that one, or
Yeah, I know what
yeah, you'd have to know one across from another. Right. Now, I do want to make something really clear for us. Okay, we took this first equation and we solved it for y, correct? Once you do that, you have to plug that into the equation you have not used yet. If you plug it back into the original equation that you started with, it's not going to work. Okay, so whichever equation you solve first, when you get to the end, you got to plug it into the opposite equation. Okay, there's going to be 3 of those problems, maybe 2 if you see a different way to do one of them on your homework. So if you would like to do those 3 problems first on your assignment so you can ask me while you're working on it, that's fine. A lot of students actually were able to get to it. We don't have quite as much time as the other classes did. Okay, so if you want to do those first few problems first, feel free to do that.